Today's topic is nitrines or amidogens. Nitrines are the nitrogen analogues of carbenes. Nitrogen analogues means similar to the carbene, or we can say comparable to carbenes. This is a representation of nitrines. These are neutral monovalent nitrogen species in which nitrogen has two unshared pair of electrons and is bonded to only one monovalent atom or a group. Neutral means it doesn't have any charge. Monovalent means it have a valency of a 1. So the nitrogen is bonded to the only one monovalent atom or a group and has a two pairs of electrons which is unshared. Now the characteristics of the nitrines. These are short-lived, highly reactive chemical species. Similar to the carbene, this is short-lived and highly reactive. Since nitrogen has only 6 electrons in the valence shell, and this has a strong tendency to complete its octet by gaining 2 electrons. As nitrogen is highly reactive because it has a 6 electron in its valence shell, and it has a strong tendency to accept a pair of electron to complete its octet. Now this represents the sextet. Thus, nitrines, like carbenes, behaves as a Lewis acid or electrophiles. Just like the carbenes, nitrines also behaves like a Lewis acid or electrophiles. Now the generation of nitrines. By thermal or photochemical decomposition of azides and isocyanates, we have alkyl azide. This bond shifting here, this lone pair is shifting here. Further we go, we have a two pairs of lone pairs and getting a positive charge. We have now 3 bonds here. In the presence of heat or light, we get the alkyl nitrine plus N2. Now the next is isocyanate. This bond shifting to N and this bond shifting to C. In the presence of light, we get the alkyl nitrate plus CO having a 2 lone pairs. Second is from nitro or nitroso compounds. This is nitro compound. In the presence of triethyl phosphate and heat, we get the nitrine. This is the nitroso compound. In the presence of same triethyl phosphate or heat, we get the nitrines. Now the type of nitrines. Nitrines has following 2 types: singlet nitrines and triplet nitrines. Now the singlet nitrines. The 4 non-bonding electrons on nitrogen are present as 2 pairs. As we know, nitrine have a 4 non-bonding electrons, and in singlet nitrine, these non-bonding electrons present as a 2 pairs. This is the representation of the singlet nitrines. Now the second is triplet nitrine. In this, 4 non-bonding electrons are present in the form of 1 pair and 2 unpaired electrons. In triplet nitrine, we have 4 non-bonding electrons, same to the singlet nitrine, but in triplet nitrine, these 4 non-bonding electrons exist as a 1 pair of electrons and 2 unpaired electrons. Now we have orbital structure. Singlet nitrine. In singlet nitrines, the N atom is sp2 hybridized. One of the sp2 hybridized orbital forms a sigma bond with a monovalent atom or group, while the other 2 sp2 orbitals contains a pair of electrons each. The unhybridized p orbital is, however, empty. As in singlet nitrine, an atom is sp2 hybridized, and one sp2 hybridized orbital forms a sigma bond with a monovalent atom or a group, while we have other 2 unhybridized 2p orbitals also, which contains a pair of electrons each, and we have another unhybridized p orbital which is empty. This is the representation of nitrine. This is the monovalent atom or a group. This is the sigma bond. This is 2 sp2 hybridized carbon which contains a pair of electrons each, and this is the unhybridized p orbital which is empty. Now the second is triplet nitrine. The nitrogen atom is sp hybridized. One sp orbital forms one bond with monovalent atom or a group. In triplet nitrines, an atom is sp hybridized, and one sp hybridized orbital forms a sigma bond with monovalent atom or a group, while other contains a pair of electrons, while we have another sp hybridized orbital which contains a pair of electrons. The other two unhybridized p orbital, that is py and pz, are perpendicular to each other and contains one electron each. And we have two unhybridized orbital, which is py and pz, which contains one electron each and are perpendicular to each other. This is the representation of triplet nitrene. This is sp hybridized nitrogen. This is the unhybridized p orbital, which is py, pz, and having a one electron each. This is the another hybridized orbital which contains a pair of electrons. Now we have stability of nitrenes. The energy difference between singlet and triplet states is usually much larger for nitrenes than for carbons. Here, the energy difference between the singlet and triplet nitrenes are larger in case of nitrenes than for the carbons. This energy difference is due to the electronegativity difference in carbon and nitrogen. This energy difference is due to the electronegativity difference. As we know, nitrogen is more electronegative than the carbon. Nitrogen is more electronegative than carbon, therefore holds its electron closer to the nucleus, which decreases energy and hence increases stability. If nitrogen is more electronegative than carbon, then nitrogen holds its electron closer to the nucleus, which decreases its energy and increases its stability. The nature of substituent on nitrogen affect both the multiplicity and the normal electrophilic reactivity of the nitrenes. Nature of substituent which are present on the nitrogen affect both the multiplicity and the electrophilic reactivity of the nitrogen. Strong pi donor substituent such as amino groups greatly stabilize the singlet as well as causing the nitrenes to exhibit nucleophilic character. Strong pi donor as a substituent on nitrenes such as like amino groups will increase the stability of singlet nitrenes and causing the nitrenes to exhibit nucleophilic character, as helps the nitrene to exhibit the nucleophilic character. Now we have reactions involving nitrenes. First is addition to alkenes. This is propene, this is nitrene. Both are added to give the propanamide. Second is addition to alkanes, 2-methyl propane. Simply this is alkane and this is acetyl nitrene. Both are added to give acetyl